Thank you for that. So my name is Krista Bryan. I am a soil scientist with NRCS. And if you guys aren't quite familiar with what all we do, kind of our main thing is helping for farmers to do voluntary conservation on their lands. In there, I'm part of Soil Survey. So we update and maintain Web Soil Survey. And that's our main charge, making interpretations. I was very glad to see the One Oak speaker talk about one of our interpretations being used. That was great to hear. So I'll be talking about to reclaim mine lands on specifically coal. So I'll start a little bit about soil survey and what we do, and then about how the coal mines reclaim their soils, and then tying it together of how we're utilizing soil survey methods with the reclamation to produce a product. A little bit about soil surveys. We're really old. We started in 1899. Actually, it was our first field investigation. First publication for North Dakota I saw this is from 1906. Kind of a fun story. Some of the initial reports were actually burned by some local businessmen trying to promote that the soil was a lot better than it was in certain areas of the state. So in North Dakota, we finished our initial soil survey. So that's the initial mapping of the ground in the early 1990s. And now we're continuing to update and maintain that product. And this reclaimed mine land work is part of an update. Nationwide coverage is supposed to be done in 2026, and that includes Alaska. So a lot of big area. And this picture up here, this is like my favorite of all time of how nice these soil scientists used to dress to do field work. So before we make a soil map, we need to understand how soils form. And to do that, we use the 5 soil forming factors known as CLORT. That is climate, organisms, relief, parent material, and time. Example of climate would be, you can consider Western North Dakota and a state such as Wisconsin. We get about 15 inches of rain a year. Wisconsin gets double that, they get 30. So you can throw a rock out here and you can hit calcium carbonate. Calcium carbonate is like leftover shellfish shells. It increases the pH. It's got some osmotic issue. It can cause osmotic issues with plants. And yeah, you can find it pretty much anywhere. But if I found some in Wisconsin, I would get kind of excited because you just don't see that very often unless there's limestone close to the surface. And that's all to do with our climate. Organisms. So a good kind of indicator one there would be the grasslands, the prairie states. We got those deep, dark organic layers, our mollisols, and that's pretty much mostly driven by those deep-rooted plants. Relief, so that would be like on a steep shoulder of a hill, you're going to have your soils be more closer to bedrock, or the carbonates might be closer to the surface. Or if you look at the aspect, if you look at the Badlands, you'll see more vegetation on the north slopes because it's a cooler microclimate and things can grow better there. Versus the southern side where that's where all the vegetation is not really well established and there's bare spots. Parent material, we have a lot of different kind of parent materials, such as alluvium, which comes from water, or residuum, which is derived from the bedrock. And even within residuum, you can have something withering from sandstone versus shale. Something derived from sandstone is going to be very sandy, a lot less water holding capacity, a lot less nutrient holding capacity than something with more clay in it. And time is what brings everything together. These processes all need time to occur. The younger soil is, the more it looks like its parent material. So we use these methods to form a landscape model in our heads and map it on the ground. Here's an example. So we have saline seep down here. You can tell that because of the white stuff and the foxtail barley. And how saline seeps form is that water will go through the hill, penetrate down, hit our bedrock, which is moraine in origin, so has a lot of salt. Picks up all that salt, follows the bedrock or coal seam down, and then outlets down here where it evaporates and leaves a bunch of salt. And we know that occurs more easily in a sandier soil. So without even digging in this hill, I can take a guess that this might be a sandier texture, especially I can't really see that. There's my pointer. Right there, there's like some brown area, like that vegetation seems a little stressed, could be from water issues. So you might find a soil like flasher there, it's shallow to bedrock or carbonates. You go down the hill, might be a little more developed, a little more organic matter, maybe some more silt and clay compared to the sand. So you might have a soil such as V-bar. Then when you get to the bottom of the hill, you're now on a run-on instead of a run-off position, so things collect here. So you might find a soil such as partial Belfield or Arnagard, which have a deeper topsoil. And Belfield is a natric soil, so it has some sodium issues associated with it. And on our maps, these saline seeps, the old county maps that were published in the 90s and before, they're marked with a spot symbol. We don't do those anymore in Web Soil Survey, so sometimes they'll be marked as like Belfield saline. Here's what a soil map looks like if you haven't seen it before. And you'll notice that there's only one area that's cropped here. And then all these areas are rangeland. And it's kind of interesting. These all have E's and F's on them. So that just means it's really steep. It's 9 to 15% slopes or greater than 35% slopes. And then here it's very flat. You got A and B slopes. And then you can also see with the soils here, Dogtooth, Jamesburg, those are natric soils again, so sodium issues. You can kind of see there's some pockmarked appearance that they can sometimes appear on the landscape that way. So this is actually glacial. So this is remnant leftover glacial material, which is why it's kind of deposited higher in the landscape and is more flat than the surrounding residual area that has been exposed to erosion for longer periods of time. All right, so we're going to apply those methods to reclaim mines. Here's an example of a soil we call Knife River. And I'd really like to point out how abrupt this boundary is right here, and then how kind of homogeneous this area here looks like. And you can compare that to a natural soil. You can see a lot more gradual movement, or gradual changes throughout the profile. So our forming factors on mine land. The climate's gonna be pretty similar because we're just talking about Southwest North Dakota. There might be some differences between like Bowman, there are some coal mines down there, versus Beulah. We'll have to wait and see about that though, but they should be, relatively speaking, very similar. Organisms, mainly people, that's our main factor here. Something to keep in mind is some of this topsoil has been stored for quite a long time, and the impacts that might have had on the microbial community in there. We're learning more and more about how microbiota is important in the soil. So that's kind of like an interesting thing. The vegetation establishes, we find it kind of similar. The main land uses out here, there's going to be rangeland or cropland, and that's going to change how the soils develop going forward. Relief, the topography is there. The mines are required to return them to approximate local contour. Basically, they put if there was a hill back, they put a hill back. It's restored back. The parent material is kind of, it's mine spoil. The things I've seen have been pretty homogeneous. They've been usually loams, clay loams, and the spoil is like a silty clay or heavy clay loam or clay. It's fairly similar. I'd say the presence of carbonates maybe a big kind of driving factor in the differences between them. And time, the thing that brings everything together. Some of the oldest that have been reclaimed in this manner I'm talking about are the earliest would have been made in like the mid 1970s. So they're only 70 years old. And if you compare that to how the soils form over thousands of years, that's just a blip, just a blip. So here is a hill slope on some reclaimed mines. This is it's more of a 10% slope. The picture kind of makes it look flatter. So it is a pretty good hill. And then you can see a wet area down here. And just to kind of explore to see how the soils changes on this hill, I took some probe samples going from top to bottom. It'd be nice if I organized them that same way, but I did not. The top one actually comes from down further below, and then this darker one actually comes from up high. There were no carbonates from the surface. Down here, they had strong to violent effervescence, and the spoil did come in at around the same period of these. Textures were the same, structure was the same. The only real difference was the darkness kind of this material. Typically, I mean, if you're thinking of soil being dark, you think of it being lower on the landscape. But for this, it's just wherever they grab to put the soil back. That's why it looks the way it does. One thing we can see, though, is this orange stuff here, and then there is some gray. I think there's one right there. That is iron oxidation and reduction. And it is caused from the removal of oxygen by saturated conditions in water. And we can see that forming in these soils. So that is something that is occurring that we can see visually on the surface and in the soil itself. So a little bit about how these soils were reclaimed. The Public Service Commission kind of oversees all of this. And in general, mine lands must be reclaimed to approximate local contour. So they have a hill, they put it back. Topsoil and subsoil, which is known as the respread, must be stockpiled separately from each other and then put back on separately. So you have the spoil, then you put the subsoil on, and then the topsoil. Typically, the topsoil is A and BW material. The subsoil, a lot of it's BK and C material. And then the spoil, a lot of it is CR material, which is our bedrock. The thickness of the respread is dependent upon the quality of the spoil material. That was done by some research back in the 1970s, around that time. And I've seen the original research. It's housed in the ARS station. It's pretty neat seeing the paper copies of it. The reclaimed land must also be returned to pre-mine levels of productivity. That's why the mines have to keep ownership of it for a while to prove that that is the case. And then the wetlands must also be restored. So those spoil characteristics, what are they? Well, the main ones are the sodium adsorption ratio, SAR, which I'll talk a little bit more later, and then the texture, which is the percentage of sand, silt, and clay within the soil. And here I have some gypsum. So we can't necessarily see sodium when it's dispersed within the soil profile, but if you see these gypsum crystals, it's just a good bet that you probably have some sodium too. They're very correlated together in North Dakota. Note on SAR. So SAR is the ratio of sodium and magnesium to other cations in the soil. For soil survey, we say that SAR 13 or more is considered natric or sodic. And that's where we say this is like the limiting factor is the sodium. Like that's what's driving our interpretations at that point. I have seen research of like 5 to 6 where you can start to see some impacts on sensitive plants. I've seen that in North Dakota. And then I have talked to people from Illinois that actually have some natric soils, and they concurred about that amount. And why do we care? Well, sodium has issues for plants being able to uptake water, but it also does this. These are called columns or muffin tops. Sodium causes the soil to disperse and puddle. So what it's causing here is the soil to kind of sploosh over and then make a hard pan and seals. It's very hard for roots to get through, very hard for me and my shovel to get through. And then when this is closer to the surface, it causes this on the surface. Plants don't really like it. Sometimes you only get a couple cactuses growing on it. Soil like this would be like a Rhodes or a Miranda. It's a simplified kind of guide to how things are reclaimed. First, we look at the texture. If it's a sandy loam or coarser, you get 36 inches of topsoil and subsoil put over that spoil. And that's due to making sure there's enough water available within the soil profile. If it's a loam or finer, which is what I've seen mainly so far, we look at the SAR. Now we have SAR of under 12. I think that that number is definitely correlated to what Soil Survey says with the 13. You need at least 2 feet of subsoil and topsoil. If it's between 12 and 20, so that's officially natric or sodic, you need 36 inches of respread. And if it's over 20, you need 48 inches of respread. All right, so like I was saying, like just looking at the landscape, I can't make a whole lot of educated guesses without actually going and digging there to see what's there. I could tell you maybe if the carbonates are closer to the surface, I can tell you the slope. Just educated guess of what I've seen on a lot of mine. I can tell you like maybe what the texture will probably be. but not as many things as I can predict on a natural landscape. So is there a way we can provide more utility for these maps? I think so. Because at least the newer mines have a record of the respread depths. So here they put 48 inches of topsoil and subsoil over the spoil. And then the spoil, therefore, is probably sodic. So we decided we're going to use this as our base. Data collection. So I did transects through the respread packages to see how consistent they are with what I could identify. Transect is just a repeated interval. So like every 100 feet, we'd stop and take a sample, describe it, and mark what it was. I also did head-ons for full characterization. That means I describe the soil's pores, I describe its color, texture, how many roots are in there, what they look like, all that. I test for surface calcareous prevalence, because I think that's going to be a pretty important factor on these, as well as through the whole profile. I also took bulk density cores. We're especially interested in the spoil. And I ran some, in my lab. And we are finding between like 1.6 and 2, actually. That's grams per cubic centimeter in the spoil material. I did send some off to our big lab in Lincoln. They have a lot more accurate methods where they do a clod method, but they're pretty backed up and I won't get results for 3 years. So we'll reevaluate once we, 3 years, we'll reevaluate once we get those kind of better samples. But as of right now, it seems like it's something we would consider a densic layer in that spoil. And you can kind of see from this picture, like the roots kind of mat and they will grow laterally along that. They're definitely not big fans. I also did pH and electrical conductivity. So I cannot do SAR in my lab. I just have a little field lab. It's very intensive. And I did do some pH and EC. Electrical conductivity is a measure of how electricity can move through the soil, which is a measure of how many cations are in the soil, which also gets at the amount of salts that are in the soil. So I'm thinking in the future, I'm going to see if I can do more of that and use it potentially as more of a screening tool to get rid of some subjectivity in telling where the spoil is. Preliminarily, what I've seen is that it does seem to be a pretty big difference between the subsoil and the spoil, those measures. So here's our soils, what we decided to call them. So if we have a respread of 24 inches, we named it box cut. 36 inches, we named it Coal Harbor. 48 inches, we named it Knife River. If it's in a wetland, we named it Dragline. If there's calcareous to the surface, or if the topsoil is less than 9 inches, we named it a calcareous phase. So you have box cut calcareous, Coal Harbor calcareous, etc. And that 9 to 8 inch range comes from our eco sites. That's when we consider something like a liney upland, where we see the carbonates impacting the plant community. And then I don't have any square butte. This was set up at the Falkirk Mine. The Bismarck Soil Survey Office actually told me that I have proposed right now. There is actually this will be changing because there's actually a whole new human order that's being created called artisols. So that'll be updated later on when that becomes officially approved. Here's this look at the soil. So here's my box cut pit. And you can see here I marked a plow layer here. And then this is the rest of the topsoil. And then down here I marked the spoil. Kind of hard to see, so I also put a probe sample here. And you can see the spoil starting right there. And then the subsoil kind of starting right there. This is the Coal Harbor pit, and this pit was kind of rough because it had carbonates all the way up to the surface, so it was a calcareous phase. The plants were not happy on this one, probably because of those carbonates and that very thin topsoil here. And from what I've read, so in this case it'd be 36 inches of topsoil and subsoil. There's not a specific ratio of topsoil you need to subsoil. I've seen recommendations of 12 inches, but I haven't seen where like you need to put at least 12 inches on. So it's just those things together. This one I just really like because it's got scoria sand mixed into the subsoil, so you can just really see those different lifts. Just very nice changes. Here's the Knife River, so that's the deepest, the 48-inch one. Here it starts at 46 inches. Here's our wetland soil, called it drag line. I looked at a lot of these last fall because it was so dry and I could get out and not make a mess of myself. The topsoil seems to be fairly deep. Like this is almost what we'd call packing. 40 centimeters would be something we'd call packing, a deep dark soil. They had active iron oxidation occurring. And wetland vegetation, lots and lots of cattails. So map unit composition, so these are from my transects. Within the box cut respread packages, and then therefore within my box cut map units. I found box cut 58% of the time and Cole Harbour 42% of the time. I'll talk about that a little bit more later. The Cole Harbour respread package, I found Cole Harbour 88% of the time, box cut 8% of the time, and Knife River 4%. So pretty homogeneous. Knife River also pretty homogeneous too, with the main being Knife River with some Cole Harbour. And dragline, I've been doing transects on, that's more of a spatial analysis kind of thing to see where those are. So the box cut and Cole Harbour kind of confusion here. And I think this is due to box cut has a lot better spoil quality, so it might just be hard to tell the difference between the spoil and then the subsoil. I also did find this in a specific part of the mine, which had more glacial till historically rather than residuum. So I'm just wondering if there was more glacial till mixed in instead of just the kind of CR material within the spoil. So it'd be interesting to see if this continues or if I get like the pH and EC thing to kind of work out to reduce some of the subjectivity there. But yeah, like here, like it's not as easy to tell where it is. I would put it about at this 29 here. You can see the blocks get bigger than up here, and then there's a color change, and then the roots kind of stop right there. But it's just, yeah, it's not as apparent as some of them are from the previous slides. All right, so we have our data, got our idea of what we're doing. Now it's time to make a map. So all these 48s, these are the respread packages. So those got merged together into one big map unit. And then I separated them by slope class. Our slope classes go from 0 to 2, 2 to 6, 6 to 9, and 9 to 15. And then after that, we put the calcareous phase on the ones that were calcareous. So that's right there. And then I put box cut and Cole Harbour together as an undifferentiated group for now. And that will work out okay, just because with our interpretations, box cut and Cole Harbour are a lot more alike than the Knife River is. They have the same HDL classification, the T values, and the same forage suitability group. So I think that'll work out pretty well. And that just means that you may find both in that map unit. And they all do have in their minor components the other map units in there, just as a smaller percentage. Wetlands and drainages were also delineated out, and they're just not on this exact map. Historically unreclaimed areas, these exist out there. They're just spoil piles. Right now, I think they're just classified as pits and dumps. And then the mine land that is reclaimed right now is just in there as mine land without any interpretations. That's why we're doing this. So we're going to put some interpretations on here for aquants, this water here. Astorthents is the vegetated area. And then we're thinking badlands, that's a miscellaneous land type. It's not a soil. And we're thinking that might work pretty well for these bare areas. The other miscellaneous land types that we have available to us, we didn't think matched very well. So that's what we're thinking right now. It's got to go through final approval still. Future thoughts are the other mineland areas. Some don't have the respread keys. So that'll have to be done more about how I was talking about earlier with calcareousness probably, and slope as being kind of the main determiners. Ecological sites seem to be developed still. Right now, they all fall into loamy. We're thinking there might be a better land planning tool than just calling it like a loamy like the natural sites. And yeah, let's talk about the EC and pH measurements, like getting some more things with that. Okay. Yeah, and we do have biota back in these mine soils as this little worm, which I may or may not have cut in half with my probe. And just in general, if you don't know much about soil survey, we make new soil interpretations if you ever need something that could help you out. Like the gal from, okay, I just remember the okay part. Oh, One Oak, yes, that's it. Like One Oak, what our state soil scientist made for her. One that I actually helped do is PFAS. So that's a forever chemical. That's a kind of an emerging contaminant. And it's not something that degrades well. So we made an interpretation about which soils can hold onto that tightly and not release it into the environment. So that's one that I personally have had some work in. We also update map units, or we can explain how the mapping works if you ever have any questions or anything like that. We do dynamic soil properties work. So that's how soils can change on a human timescale. And we also do a lot of education and outreach things right here, which my predecessor Jeannie's out here with some kids. So yeah, this product is slated to come out this September with the annual soils refresh. I still have to get everything okayed with my regional office, and then we're going to do a meeting with the PSC, and then with the mine to make sure to get the final, like if they have any concerns or anything before we put it out.